Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former Professor and Head of the Department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series for the BSc Honors Physics students, and in the semester 4 and in the paper which has a chapter on optics, we are passing through especially wave optics, and we are talking about interference in the lecture number 16. And the contents of this lecture will be as follows: Fresnel biprism, experimental arrangement for determining the fringe width, expression for the distance separating the 2 virtual sources. In the last lecture, we saw how interference bands are being formed in the Young's double-slit experiment. For the interference pattern to be obtained, what do you mean by interference pattern? You mean the formation of bright and dark bands on the screen. How do you get the bright and dark bands? You have a source, then you got 2 slits. The light passing through the 2 slits, they act as 2 coherent sources, and the light coming from the coherent sources interfere and give rise to the interference bands or the alternate bright and dark lines or bands. The important point is you have to have 2 coherent sources, and also we saw the condition under which you will be getting a bright band or a dark band. Essentially, the point is how to get 2 coherent sources. For that, you make use of what is called a Fresnel biprism. To start with, you will have a single source, and you will be getting 2 virtual sources from the single source, as you will be seeing in the diagram to follow. The Fresnel biprism is a biprism which is made up of a thin glass plate. You take a thin glass plate, and in the normal prism which was used by Newton or Hooke to obtain the different colors, Vibgyor, you have the equilateral triangle like thing, but here you have a glass plate and one face will be plane, the other is making an angle something like 179 degrees. It has been grounded, the grinding has been done on one of the faces. One of the faces will be straight, the other face will be, you make an angle and it will be almost plane. The angle subtended by the 2 faces will be 179 degrees. If the angle is 180 means it is plane. When light is incident on the prism, the emergent ray appears to come from a virtual source S1 that is shown in the following figure. Thus, Fresnel could create 2 virtual sources S1 and S2 by constructing a biprism. This is the biprism, right? This is the angle that is 179 degrees, right? You have got biprism here, and the light coming from the source S1, and you got S here and you got S1 here. The point I want to tell you is you have, supposing you got two prisms, if you have got a source, for this source you will be having two virtual sources S1 and S2. The point to be remembered is you got a source S here, this is a biprism, you got two prisms. The two sources S1 and S2 are the virtual sources which are obtained from the single source S. Why should you get two virtual sources? You have to have two coherent sources in order that the interference pattern is seen on the screen. This is the interference pattern. You got a bright line followed by no intensity. The region can be considered as a dark band, again a bright band, dark band. You should also remember the distance between two bright bands, beta, will also be equal to the distance between two dark bands. So this is beta here, right? This is 2 beta. Anyway, the point is this is beta, the thickness of bright band is beta, dark band also is beta. The distance separating the two bright bands is also equal to the distance separating two successive dark bands, that you call it the fringe width or the band width, and we got the expression in the last lecture for beta. How do you define beta? Beta will be equal to capital D by small d into lambda. What is capital D? This is capital D. The distance separating the source, this is the source S, and the screen here, right? The distance separating the source and the screen, that is your capital D. Okay. The distance separating the two virtual sources, you remember S is the source. Now using a biprism, as I showed you here, you have got a biprism. What for you are using biprism? From a single source you get two virtual sources, S1 and S2. They are the virtual sources. Distance that separates the two virtual sources is small d, and this is a capital D. And then beta, as we saw in the last lecture, will be this capital D by small d multiplied by the wavelength that comes in the numerator. So essentially what do you do from this experiment? This experiment enables you to determine the wavelength of the monochromatic source. S is a monochromatic source, as I told you in the last lecture. It may be a sodium vapor lamp. The wavelength is a thing that cannot be obtained very easily. The wavelength of the source is 5893 into 10 to the power of minus 8 centimeter. How will you measure 10 to the power of minus 8 centimeter? You can use a scale, can use an ordinary scale or a microscope. 10 to the power of minus 8 centimeter is such a small quantity. The wavelength of the light source is so small, such a small quantity can be accurately determined using the Fresnel biprism or the air wedge, about which I will be talking in the lectures to come, and also the Newton's rings. These are the experiments by which a wavelength can be obtained. Apart from wavelengths, and other things also can be measured. Therefore, you have the small d here, capital D here, and you see the expression for beta in the last lecture. P is the prism, you got a biprism here, and S1, S2 are the two coherent sources which are obtained from the single source S, that is your sodium vapor lamp, and D, the distance between the sources and the screen. Small d, as you know by now, it is the distance that separates the two virtual sources. A convex lens of short focal length is placed in between the slit and the eyepiece and is adjusted such that one obtains a short pair of images in the field of view when the lens is kept near the biprism. Measure the distance between the two images, which is d1. So what I mean by this is, you have a lens here nearer to the biprism, then you get what you call as the enlarged image. Now the aim of determining d1 and d2 is to measure your small d. The small d, the distance between the two virtual sources, will be expressed in terms of d1 and d2. What are d1 and d2? D1 is the, you get a what you call a enlarged image. For the two virtual sources, you will see in the through the eyepiece, you will be getting two images separated by a larger distance, whereas in the other case, when the lens is kept here nearer to the screen, you get a diminished image. Diminished means the distance separating the two images will be smaller. The enlarged means it will be larger. The enlarged one is the D1. You put the eyepiece can be adjusted so that the crosswire coincides with this line and then with this line, that is your D1. Then this is a D2. How do you get D1 and D2? The lens L1 is kept nearer to the biprism, then you get an enlarged image. On the other hand, when the lens is kept nearer to the screen, then you get a diminished image. Both D1 and D2 can be measured using a microscope, using making the crosswire to coincide with this line, take the reading and then move the crosswire and make it to coincide with the next line, and how far the screw has been moved can be seen from your vernier scale and all, and main scale, vernier scale. Therefore, your D1 is a measurable quantity. In the laboratory, D1 can be measured. D2 also can be measured. So, measurement of the distances between the two virtual sources is the important thing that we are going through. And so, the frontal biprism, as I told you, if U is the distance of the slit and V is that of the eyepiece from lens, then the magnification is V by U is equal to D1 by D. The lens is then moved to a position nearer to the eyepiece, where again a pair of image of the slit is seen. The distance between the two sharp images is again measured, that is your D2. That is the lens is moved away from the biprism. Then you get D2, that is the one that you measure again. So, that is D2. Magnification in this case is again V by U will be D2 by D. Note that the magnification in one position is a reciprocal of the magnification in the other position, multiplying the above equations. That is, you got V by U is equal to D2 by D, that is here D1 by D. So, by multiplying these two, you get D1 D2 by D square is equal to, D is common, D1 D2 multiplied by D square is equal to 1, or in other words, the important quantity D. What is D? D is the distance between two virtual sources which can be easily measured. So, the distance between the two virtual sources turns out to be square root of D1 multiplied by D2. So, what are D1 D2? As I told you, how do you measure the distance between the two virtual sources? These are the source S, and distance between the two virtual sources is measured by interposing a lens and obtaining the enlarged image D1, the distance between the two lines D1, and similarly keeping the lens here farther away from the biprism, you get what is called a diminished image. You measure D2. By measuring D1 and D2, you get the important quantity, namely small d, the distance that separates the two virtual sources. Now, since you know small d, you also know capital D, hence this enables you to determine the wavelength of the light source. Now, we have here your beta. What is beta? It is called the fringe width. That will be, as I told you, capital D by small d into lambda. What is meant by fringe width? Fringe width is nothing but x m plus 1 minus x m. What is x m plus 1 and what is meant by x m? X m plus 1 is the position of your crosswire when you make the you have the crosswire to coincide with the mth bright band, you take the reading. Then you make it to coincide with the m plus 1. This is the mth bright band. This is the m plus 1th bright band. So, you take the reading corresponding to the case when the crosswire is coinciding a particular bright band or a dark band. That you call the mth band. The next band will be obviously m plus 1th band. You make the crosswire to coincide with this band, that is your xm. Then move the eyepiece, crosshair moves, the crosshair is made to coincide with the next bright band, that is the m+1th bright band. Take the reading, and the difference between these two, as you know, the distance that separates two successive bright bands is the bandwidth beta. Therefore, if you know beta, you can measure lambda. Let us have a short break now. Welcome back after the break. Now, what we are trying to do now, number one, you make use of a biprism to get two coherent sources. Why should you have two coherent sources? Only if you have got two coherent sources emitting light at the same wavelength, having no phase difference, then only you will be getting stationary interference pattern. This is the interference pattern that we are getting here. How do you get the pattern? By creating two virtual sources. That is the reason why you make use of the biprism. I think it should be clear. So, you make use of a biprism to obtain two coherent sources S1 and S2. Make the light coming from the source S1, you have the light coming from S1, and similarly you have got the light coming from S2. You see the region here where the beams are interfering. So, you get the pattern, difference pattern in the region EF. In the region EF where the light beams are interfering, you get the bright and dark bands. You get a bright band, dark band, bright band, dark band, and from these bright and dark bands you can measure what is called beta. Beta is the bandwidth. What is bandwidth? The distance that separates two successive bright bands or two successive dark bands. By measuring your beta and make use of the relation that we saw in the last lecture, namely beta is equal to d by small d into lambda. What is d? D is the distance that separates the two virtual sources on the screen, that is your capital D. Small d is the distance that separates the two virtual sources, and lambda is the wavelength, that is equal to the bandwidth. So, this is a very important relation. Now, the bandwidth is the one that can be obtained, as I told you just now, by making the crosswire to coincide with the m+1th band and the mth band, by separating the two distances, right, by measuring the distances between the reading that you take for the mth band and m+1th band, that difference will give you beta. So, beta is a thing that can be easily measured, right. So, having known beta, capital D will be, as I told you in the last lecture, will be about a meter, about 100 centimeters or 90 centimeters. It can be adjusted, that it is in your hands. Small d is a thing cannot be adjusted, that is the distance that separates the two coherent sources, that can be measured. How it can be measured, what is the relation and all, we saw just now. D is equal to square root of d1 d2. So, if you know small d, if you know capital D is a thing which can be easily measured, lambda can be determined. So, this is an experiment that you do or perform to estimate the wavelength of the monochromatic source. This is a very important experiment. Fresnel biprism experiment is an important experiment which enables one to determine the wavelength of the monochromatic source. You determine the wavelength of the monochromatic source by making use of biprism and by constructing two coherent sources and making the two coherent sources to interfere with each other, right. That is important. The two coherent sources that you get, you have two coherent sources S1 and S2. The light coming from S1, you see here, you have got arrow here, light is coming from here to here, then the light ray goes straight, right. There is a region that is covered by the light coming from S1. Similarly, from S2, light goes up to A, and then the direct ray will pass through to F. This is the region, the shaded region, the stripes that you have, right. That is the region where the two beams cross each other or interfere with each other. So, this is the region EF that you have got on the screen is the region where the interference should be obtained or the interference pattern can be expected. So, you get the interference pattern, right. So, having got the interference pattern, you can determine the wavelength of the light source. What is important is getting from a single source the two coherent sources. How do you get the two coherent sources? You make use of a Fresnel biprism. Instead of biprism, can we think of some other method for obtaining two coherent sources? Here comes another method given by Lloyd. So, it is called a Lloyd's single mirror. So, you have got a Lloyd's single mirror. In this case, in order to obtain, here again the aim is the same. Instead of using a Fresnel biprism wherein you try to get two coherent sources, the same thing can be obtained using Lloyd's single mirror. So, in order to obtain two virtual sources S1 and S2, Lloyd used a plane mirror. A cylindrical wavefront coming from S1 falls on the mirror which reflects a portion of the incident wavefront, gives rise to a virtual image of the slit at S2. Now, look at the diagram. This can be understood by looking at the diagram. A cylindrical wavefront coming from S1, where is S1? You got S1 here. This is a single mirror. You got a mirror here, right? The single mirror. Light coming from S1. S1 is here, right? Coming from S1. Light is incident here. The whole region, light is falling on the whole region. The one of the rays, the other ray, the whole region is illuminated. The light ray which is illuminated here, this light ray is getting reflected. Okay, this light ray is reflected in this direction. One of the light rays goes up to E, the other light ray goes in this direction up to F, and then you have S2 here instead of S1. From S1 you get a virtual source S2. S2 is a source from where light will be coming and will be traveling along this direction E, right? And so similarly you will be having a light ray coming from S2 and incident on M, and so S2 is a source created from S1. S2 is the virtual source is obtained from S1. So another portion of the wavefront proceeds directly from the slit S1 to the screen. That is, this light source is going directly to the screen, whereas the other source S2 is the virtual source we obtained using the Lloyd's single mirror. So Lloyd's single mirror is also capable of obtaining two coherent sources. So slits S1 and S2 act as two coherent sources. C is the point on the screen which when produced backward, where is C? C is the point on the screen which when produced backward towards the sources, you have the equal distance from S1 and S2, and here again the bandwidth beta will be capital D by small d into lambda, the same as what we saw in the earlier portion for the biprism. The wavelength is determined using the above expression again. The wavelength is obtained by the same old expression, but the method of obtaining two coherent sources using a Lloyd's single mirror is different from that of the biprism. Let us now move on to what is called interference in thin films. What do you mean by thin film? You see, when you walk on the road, some petrol or oil is spilled on the road, then you see some color because you have a thin film or a thin region of oil found on water, right? A small layer of oil which is spilled on water, that is this layer is the so-called thin film, or you consider a soap bubble. You have a soap bubble, and soap bubble will be again, you have the thicker the soap bubble. You got a bubble here, you got air here, you got a bubble, right? You got a bubble, and the bubble appears to be colored. The coloration is due to interference. So when you talk of interference of thin films, it means again the interference pattern that one has due to the thin film or a thin layer of oil that is spilled on water in a road. In the road you got water, on that automobile spill some oil or petrol, and there appears to be, you see a color, right? It is called colors of thin films, because you got a film and the coloration is due to the interference phenomenon. What we want to tell is the varied colors observed when white light is incident on, you see the sunlight is falling, when you walk on the road you got a thin layer of oil or petrol which is found on the surface of water. You may be wondering why it is colored. The coloration is due to the interference of white light that is incident on the oil film. So the varied colors observed when white light is incident on such films result from the interference of waves reflected from the two surfaces of the film. What do you mean by two surfaces? One is that you got a layer here, layer of petrol or layer of oil. The layer has got an upper surface, layer thickness is some micron size. There will be layer will be there, a thin layer, and the upper surface and the lower surface. The light is reflected on the upper surface, light is reflected by the lower surface. These two light beams will interfere, and the interference will lead to either different colors. Consider a film of uniform thickness T and the index of refraction N, because the oil will have a different refractive index compared to air. Let us assume that the light rays traveling in air are nearly normal to the two surfaces of the film. So when white light is incident on a thin film, you will be getting colors. Then again the colors that you get again on soap bubbles is also due to interference. You see beautiful color, and these upper surface, the lower surface. You got a thin layer here, right? Thin layer, light is incident on the upper surface, light travels through the film and is reflected at the bottom of the layer and gets reflected, and these two beams will interfere, giving rise to the phenomenon of interference. This is a pattern that you see on the road. When you walk on the road, you have the road here, you got a thin film of oil or something, a pattern of colored light formed by interference between white light being reflected from the surface of a thin film of diesel fuel on the surface of water and the diesel water interface. This is the diesel water interface. When an automobile is going in the street, some amount of oil would have been fallen on water. So the water oil interface, you get colors that you would have seen normally. So the light is incident on the upper surface of the thin film, getting reflected, and now the light is partially getting reflected and partially it is refracted, and the refracted beam again will be getting reflected by the bottom surface of the film, and then it undergoes again refraction. These two light rays which are going from D and C, so these two light rays that are shown by arrows, the light rays getting reflected by the upper surface and lower surface of the film of thickness D, depending upon the manner in which the two light waves interfere, you will be having either constructive or destructive interference. The summary of this lecture is the following. The distance between two virtual sources are obtained by a biprism. It is measured in terms of D1 and D2, the enlarge and diminish images. Instead of using a biprism, Lloyd used a single mirror. It is also capable of producing two virtual sources. Colors of thin films is due to the phenomenon of interference. Here comes the questions to test your knowledge. Question number 1. How do you obtain the enlarge and diminish images in the case of a biprism? How are they related to the distance between the two virtual sources? How do you obtain the virtual sources using the Lloyd's single mirror? What do you understand by colors of thin films? With this we come to the end of this lecture, and in the next lecture we will continue with the colors of thin films. Thank you.